and welcome to mathlib, abelianization.lean. Here it is, and this is not the volume is quite low. I'm using the right mic. Right, I'll speak up. So welcome along, everyone. This is abelianization.lean. This is abelianization.lean in mathlib, but it's not the mathlib that you normally work with, right? I'm on a branch here. I'm on the quotient group refactor branch, and the thing about the quotient group refactor branch is that it doesn't work, right? We broke mathlib. If I just click on sulof.lean, there we go. It's, the orange bars are there. It's compiling, and there's some errors. There you go. There's 10 errors. So this is mathlib and it's broken. And the reason it's broken is that me and Scott Morrison are breaking it, right? And we're breaking it for fun, and then we're fixing it. And we're not breaking it for fun. We're breaking it because, look, this line here, abelianization.lean. So, is audio okay? This line here, this abelianization.lean, what does it import? So, I mean, yeah, let's read this file. Let's read this file. What does this file abelianization.lean do? Okay, great. We're supposed to be defining the functor from grup to ab, which is the left adjoint of the forgetful functor from ab to group. So what does that actually mean? We're trying to write down a function that takes in a group and spits out an abelian group, right? That's what we're trying to do. And do you know, there's already a function in lean which takes an abelian group and spits out a group. And guess what that functor is? That functor is the do-nothing functor, the forgetful functor, right? Every abelian group is obviously a group, so there's a functor from abelian groups to groups. Okay, but weirdly, there's also a functor the other way. Given a group, you can make an abelian group. And how do you make the abelian group? You do something called the abelianization of G, and you quotient out by something called the derived subgroup, which is the normal subgroup generated by the commutators. And that's the theory of the abelianization of a group. And the abelianization of a group has some functorial properties. You see, it's these two functors are adjoint, and that translates down into some very concrete statements about what this construction will do. And the big problem with this file is absolutely great. It's abelianization.lean. It all works file. It was written 2 years ago by Kenny and Michael. So Kenny is an undergraduate at my university. And the big problem with this is that it's got a deprecated import, right? So let's remove the deprecated import, okay? Because what we're actually doing on this quotient group refactor branch is we're trying to fix lean so it doesn't use any deprecated stuff, right? What's happened here? What's happened here is there's two ways. This is an implementation issue, right? Implementation issue. Implementation issue warning. Okay, and the warning is we used to do subgroups using something called is subgroup there, and we now do them. Oops, let's get back to shouting. We now do them using subgroup, right? So this is a run through of some levels of a computer game, but actually I'm playing the computer game in hard mode because I've actually literally just broken the computer game, right? So we've imported out the deprecated problem, and now our goal is to make this thing compile, right? That's what refactoring is. This file is broken. We're going to fix it. We're going to make it compile, and then I'm going to push the fixed version to GitHub, and then we can go on to another file. And there's like about 10 files that don't work so far. So all we have to do is do 10 worlds, right? This is a abelianization world, okay? We're playing the refactor group theory game. This is a abelianization world. And by doing this, what I've done is I've just attempted to start playing the game, but unfortunately, we now have 6 errors, right? 6 errors, that's a lot of errors. Okay, so the first thing we're going to have to do, let's start reading through the file and let's see what it says. And then when we come to the errors, we'll work out what the problem is and we'll fix the errors, right? So that's what we're going to do. We're going to read this file, and when we get to an error, we're going to fix it. So this just says, mathematicians ignore this, right? Mathematicians ignore this. So let's comment out imported deprecated. right? Mathematicians can ignore this. This is something to do with universes, okay? This says let G be a group, right? There. And this group G is in universe U, okay? Because there's the U, right? We don't really need G. We don't care which universe it is. We're mathematicians, right? We can just leave that. We could just remove them. I could do a global exchange of all type U to type, and it would remove them all. So G is a group in a certain universe if you happen to be doing mathematics with universes. And now here's the next line. The next line says we use some deprecated stuff, so we're going to delete that, right? Because we're going to fix it. The next line, let's see what's happening here. The next line says that the commutator of a subgroup, here's some mathematics, right? Here's some mathematics. This should have a definition, right? So that the mathlib people have been bad here, right? This is bad mathlib. This is bad style, okay? This is a definition. So it should have a doc string, okay? Because this is a creative piece of work, right? This is part of the creativity of mathematics, and we need to explain to humans what's going on here. So what's going on? The commutator subgroup. This is a good idea. This is an important definition. The commutator subgroup of a group G is the normal subgroup generated by the conjugate. Is the normal subgroup generated by the conjugates. I should say the commutators. The commutators, and what are they called? They're called things like PQ, right? Which is defined to be P times Q times P inverse. Did I get it? I didn't get it. Times P inverse times Q inverse. There, and I should put that in there. Put that in quotes, and let's get rid of. Yeah, that'll do. That looks like a perfectly good doc string. And now you can look and see what the definition is, and the definition is exactly that, right? The definition is that the commutator subgroup. The commutator is. This says let G be a group. The commutator of G is the following subgroup of G. It's the normal closure of the following set. The set of x's which are of the form P times Q times P inverse times Q inverse. Okay, so that's the normal definition of the commutator subgroup. Right, and now what's going on here? The abelian, and again, this is bad. This is another definition, and they haven't got a doc string, so let's put it in. The abelianization of G. The abelianization of G is the quote of G. Is the quotient group. Is the quotient of G by its commutator subgroup. There we go. So we're making mathlib a better place, right? There's the definition of the abelianization of G. It's the quotient of G by its commutator subgroup. And now here we're in the namespace. Here we're in the abelianization namespace. So in here we will prove theorems about the abelianization of a group. The abelianization of a group, okay? And now the next line, we have some error. Mathematically, is the closure necessary? Are the elements of that form, they're closed under conjugation, but they're not a subgroup, right? Look at subgroup normal closure. So the input of subgroup dot normal closure is a set, right? That's the function we're using. If I hover over subgroup dot normal closure, you can see its type. That first line, it says let G be a group, and then this function inputs a subset of G. That's set G. That means a subset of G. So the input is a subset of G, and the output is a subgroup of G. So lean specifically wants a subset, and it will then take the normal closure. It will then take the smallest normal subgroup generated by that set. And I think that I think there are examples known where this set of elements isn't even a subgroup. If it were a subgroup, it would be normal, but it's not a subgroup in general. So there's the abelianization of G. And now here's the first error. Local attribute instance. So the error is on normal subgroup to his subgroup. A normal subgroup to his subgroup is undefined, right? And you can see what's happened here is that you can see that word is subgroup, right? This is something to do with is subgroup, and is subgroup is exactly the thing that we're deprecating. So let's just remove that and hope it doesn't cause any problems, right? Whatever it is, we don't want it. While we're here, because we're not just fixing it, we're reading it. While we're here, let's read this. What does quotient group.leftRel mean? And why are we making it an instance? What this line says is it says, we are going to tell lean that in this file, that's what local means, in this file, every single group has got a canonical equivalence relation on it. That's what this says. Every single group has got a canonical equivalence relation on it, and it's going to be the canonical equivalence relation coming from the commutator subgroup. Because they think that it will make quotients easier if we just say, now let's quotient out G by the obvious thing that we always quotient out G by. So that's the idea of this attribute, and I don't know if we need it. I would comment it out to see if it breaks anything, but we still have 4 errors, so we're not in a position to comment things out yet. So now let's have a look at the next line. This next line says that the abelianization of a group is a commutative group. So that's kind of interesting. So let's see what needs to be done. What needs to be done here is that there's a begin-end block, right? There's a theorem here. There's a proof. So the fact that this thing is a commutative group, this needs a proof, right? We should be able to see. Can I see what's going on here? Oh no, those are just the errors. Let's leave the errors. What about if I click round here? Ah, bingo. Here we are. Look, I've clicked around, and I've finally found a place where lean's prepared to tell us this is the new widget tactic state. I've clicked around and I've finally worked out a way to see what lean is doing. We're trying to prove that this abelianization is a commutative group. We know it's a group, right? We've defined it. You know, this is a group quotient, right? You can't tell that. Look, this is quotient group.quotient. We've quotiented out the group by the commutator subgroup, and what we have is a group, right? So abelianization D is definitely a group, right? This is a group by definition, but the question is, why is it commutative? And there's only one thing we have to prove, right? And that one thing that we have to prove, we can see here, we can see here, we can see here. Where did I see it? I saw it there. That's the thing we have to prove. Let x and y be in the abelianization of G. We have to prove that x times y is y times x, right? That's the next step of this. It says it's an instance, but it's not really an instance. This is a theorem, right? This part of the story is a theorem, and we've got to prove. What have we got to prove? We've got to prove this theorem here that says if we take any x and y in the abelianization of G, then x times y is y times x. But now the problem with this theorem is that we now need a name for something in the abelianization of G, right? We want to lift it. We haven't actually got any elements of G, right? If you like, an element of the abelianization of G is a subset of G, right? It's an equivalence class. It's a coset, right? X is an actual coset. It's not an element of the coset. X and y are cosets, and we need to check that x times y is y times x. And the way to work with cosets is say it's a coset. So let's write it in the form h times a, where h is the commutator subgroup. And we've got this other coset y. So why don't we write that as h times b? So there we go. And now what happens if we do that? Now this says great. So quotient.mc primed is lean silly notation for the coset. So this now says the coset of A times the coset of B equals the coset of B times the coset of A. And now we have to, this is still a statement about the cosets, okay? So let's just play around. Let's do this. And actually this has done something funny. This has changed it into a question about G, right? There are no quotients anymore. We applied some fundamental theorem, we applied a universal property of quotients here, and the goal has now said, you see x and y aren't there anymore, right? They're gone. See, we can clear x, and we can clear y. Clear x, y. This is no longer a question about x and y. This is a question about a group G. This says, let G be a group, let A and B in G, okay? Try and prove that A times B is equivalent to B times A. Where the equivalence relation is what? It's this thing here. We put an equivalence relation on G, and the equivalence relation we put on it, it's hard to read, but let me just tell you what the answer is. It doesn't matter how it did it. The equivalence relation we put on G is that x is equivalent to y if x times y inverse is in the commutator, right? So that's what we've got to prove. we've got to prove that x times y, we've got to prove that AB times BA inverse is in the commutator. And what is the commutator? The commutator is defined to be the normal closure of something. Okay, and there's a theorem about normal closures. Look at this theorem here. This theorem here that I'm hovering over, subgroup subset normal closure. It says that if S is a subset of G, then S is obviously a subset of its normal closure. It says S is a subset of its normal closure. So we're trying to prove that something is in the normal closure. And why don't we just say, because the normal closure of a set obviously contains the set, why don't we just prove it's in the set? So here we are. We've got to prove that AB inverse times BA, right? This is the definition of the equivalence relation. AB inverse times BA is in the commutator. We could do that here, right? Just to make this absolutely clear. Maybe I'll just, this thing here, this goal here that looks like an equivalence relation, it's this goal here. It's show that this thing here is in the commutator subgroup of G. Right? There we go. See, that's compiled, right? I've still only got 4 errors. We've got 4 errors, but we haven't got to the errors yet. So that's what the goal really says. It just said it in a slightly weird way with an equivalence relation. We're trying to prove that this thing here is in the commutator of G. And now let's apply the fact that obviously, the commutator is generated by a set, and it would suffice to prove that it's in that set. So we've got to prove that AB inverse times BA is in this set. Right? So what have we got to prove? We've got to prove that there's P and Q in G such that P times Q times P inverse times Q inverse is this. Let's try de-simping this. There, we've got to prove that there exists P and Q in G such that P times Q times P inverse times Q inverse is this thing here. AB inverse times B times A. Let's just multiply this out in our heads, right? AB inverse is B inverse times A inverse. So P is going to be B inverse and Q is going to be A inverse, right? So we use B inverse and we use A inverse. And now look, we've got to prove that, right? That just says that B inverse times A inverse times B times A equals B times A, right? That's obvious, okay? Except it's not, it's true by definition, right? So we should go REFL, right? It's obviously true by, but it's not true by definition, okay? Why is this not true by definition? B inverse inverse is not equal to B by definition. B inverse inverse is equal to B because of a theorem in group theory, a very easy theorem in group theory that can be solved by simp, right? And A times B inverse, this is B inverse times A inverse, but that's another theorem in group theory. And we apply those theorems, and even then we're not done because the brackets are all in the wrong place. And we need to apply associativity of multiplication, which is another theorem of group theory. Okay, so we're not done. This is not true by definition, but they're all true by easy theorems in group theory. So why don't we just use the group tactic? Let's put group here. And it hasn't worked because we haven't imported the group tactic. Let's import tactic.group, just because it makes life easier. Okay, let's import tactic.group, and now let's go back to our proof. There we go. We used B inverse, we used A inverse, and now we've got to prove this, and this is completely trivial. The group tactic does it, and we get goals accomplished. We can delete these last 2 lines, right? We've made that proof more readable. So the abelianization is a commutative group. Great. Let's press on. This theorem here says that the abelianization of G is non-empty, and indeed the proof that it's non-empty is it's got an identity element. So there you go. Yeah, exactly. This is true by calculation instead of being true by definition. It's not true by definition. It's true because of an algorithm, right? There. An algorithm to solve questions like this. There. If you're interested in building, so here's an ad actually, advert. Interested in building an algorithm. Interested in building an algorithm to solve questions in group theory like this. Well, I've got go and do my exercises in my Wednesday Lean for the Curious Mathematician session. In Lean for the Curious Mathematician, I gave a talk on Wednesday, and in that talk I proved all the right lemmas, and then I explained how to make the tactic. Is group more efficient than simp? Simp doesn't work, that's the problem. Does it work? You see, simp doesn't quite do it, because simp doesn't know associativity of multiplication. So group is just nicer, I don't know. So now what's going on? So here's a function called of, and again it's a definition, and again there's no docstring. So let's make it so of is what? Of is the canonical projection from G to its abelianization. There. That's what it is. It's the obvious map from G to its abelianization. Its definition is incomprehensible. Don't worry, it's the obvious thing, right? We're defining a map from G to its... The abelianization of G is a quotient of G, right? Simp-Malloc is just harder to read. That's all. Yeah, it should be Simp-Malloc. All right, I'll put, Simp-Malloc. I mean, who even cares? It's a proof. I care about the proofs. I don't care about the techniques. I just want the proofs. So now we have of. Of is the map from G to its abelianization, and we use something to do with quotient groups to make it. And we had to prove some theorems, and they were all true by definition. So now we've got a map of. In maths, we would write G bar, right? If I've got G in G, and then the image in the abelianization of G could be called G bar or G ab or something, or ab of G. For some reason, we've called it of. So here we are in of, and now here's our main theorem. We're going to prove a main. This is all we've got left, right? So what's going on here? So we built. So far, we've built the abelianization. Can I do this? I wonder. No. What? I can't get the. No. This. Bingo. And then this. So far, we built GAB and proved it's an abelian group, right? That's what we've done so far. That was the last thing we did. We've defined a map from G to GAB there. So we defined a map, and we defined of, and it goes from G to GAB. There. That's what we've done so far. So now let A be an A. So this says let A be an abelian group. That's what line 70 says. Let A be an abelian group, and let F be a group homomorphism. Let F be a group homomorphism from G to A. Okay. So now what we're doing is that this abelianization of G is not just a random abelian group that happens to be a quotient of G. It has a universal property. You see. We've got a group homomorphism from G to its abelianization, and we've proved that the abelianization is an abelian group. So what's happening here is we've got another group, A. A could be the abelianization of G, but it might just be a random abelian group. And we've got a map F from G to A, so F could be of, right? But actually, if A is a random abelian group, then F won't be of, because of goes from G to its abelianization. So what we've got here is we've got all the stuff that of satisfies. Okay, we've got all the stuff that of satisfies, and what we're going to do is we're going to prove that the abelianization has some sort of universal property, and the universal property we're going to prove is down here, right? It's this thing here. It's this lib. This is where we're going, right? Goal. If G to A is a group homomorphism, is a group hom, then it factors through GAB, right? That's what that theorem says. That's what that theorem says. So this is the theorem we're trying to prove. You see, this is the universal property of the abelianization. There, and this will be the proof. This will be the proof that it's an adjoint functor, I would imagine. Or this would be some key part. I mean, I haven't really thought about adjoint functors, but this sounds like a very adjoint functory thing. But before we get to our goal, we have a problem, right? We have a problem here. We have our first error. Where's our first error? Let's turn errors on. Our first error is unknown identifier is group hom mem cur. Our first error is on line 74. So our first error is in this block here, right? So our first error is in the proof of a lemma, okay? So we've got a lemma here. Lemmas are fun to prove, right? This is the fun part, right? Proving this lemma is like solving a video game, right? It's like solving a puzzle. you know, it's solving a computer puzzle. So let's just comment this proof out completely. There, we've commented out that proof completely, and let's try and prove it because it didn't work, right? At some point in this proof, why doesn't that proof work? Look, I can make that proof work again. I can make that proof work again by just uncommenting. I deleted some deprecated import. The reason this lemma used to work is because we had a deprecated import, okay? And now we're going to have to fix this lemma. So let's have a look at this. Fix me. Let's not worry about the fix me. Let's put the fix me back. Let's try. Oh, what am I doing? Begin. Sorry. End. Right. And now let's do exit. There. So now what's happened is now we're in puzzle game mode, and the reason we're in puzzle game mode is that there's no errors. Look. There's 2 warnings, there's no errors. And the 2 warnings are very easy to understand. The first warning says we cheated with a sorry, and the second warning says we stopped early with an exit. Okay? So we need to get rid of these 2 warnings. Let's get rid of this warning. Let's prove a theorem. Let's prove a theorem. Let's see what the theorem says. The theorem says that the commutator of G is a subgroup of the kernel of F. Right? That's what we've got to prove, apparently. We're defining a map from G to an abelian group. We've got to prove that the commutator of G is a subgroup of the kernel of F. So why is that true? I mean, that's an interesting maths theorem. Why is that true? Let's go through the maths proof first. So need to prove, let's just do this. So what have we got? We've got G a group, A an abelian group, there, and we've got F from G to a group homomorphism, right? There. And importantly is that A is an abelian group. F from G to a group homomorphism, and we want to prove that the commutator of G is contained in the kernel of F. Right. So why is that true? If you think about it, the commutator is generated. I mean, here's the proof. Right, maths proof. Commutator is generated by things of the form x, x, y, x inverse, y inverse, right? There. Apply f there, and we get f of x times f of y times f of x inverse times f of y inverse. There. That's what we get. And this is an identity in an abelian group, right? And this is in an abelian group, so it's true. So it's 1 there. So there we go. So that's the maths proof. Now let's try and do the lean proof, okay? Because we need to do this lean proof to refactor our. So actually, let's get inspired by the lean proof that broke. The first thing it does is it invokes a function called subgroup normal closure len normal. So let's just apply that without even knowing what it is. Apply that. There you go, and that's worked. And now we've got 2 goals. Okay, so this looks good. And the 2 goals, and I want to put my sorries back in. It's always nice to have sorries. So we've applied a theorem. We don't even know what it did, and it's made progress. And the theorem is subgroup dot normal closure len normal. Okay, and let's hover over that theorem. And this is what it says: the normal closure of S is the smallest normal subgroup containing S. And here S is a set, right? The normal closure of S is the smallest normal subgroup containing S. So we were trying to prove that the commutator subgroup was contained in the kernel. And what we're saying is the commutator subgroup is the smallest normal subgroup generated by a set. Okay, so why don't we just try and prove that the set is in the kernel instead? Because if the set is in the kernel, then the smallest normal subgroup generated by the set will obviously be in the kernel, assuming the kernel is normal, right? So we've applied this, and now you can see we've got 2 goals. The first thing is, why don't you prove to me that the kernel is normal? And the proof that didn't work says by apply instance. So why don't we just try that? Why don't you just try apply instance? because this is just a standard fact, so it's in there somewhere. There we go. The kernel of a group homomorphism is a normal subgroup. I don't want to waste my time looking around the library trying to find that proof, right? So now here we go. And now this is the part that broke, right? Well, I don't know if you looked, but the actual error was here when we had a red error. We've got no errors currently. So the part of the proof that broke that worked started with this lambda x pqw, and lambda is just computer science for intros. So it's intros x, and now let's see what the goal is. Intros x, and the goal is if x is in some crazy set. Let's try simplifying what it says. Dsimp. It says if x is in some crazy set there, and it's the set of x such that there exists a pq such that x is p times q times p inverse times q inverse. So in other words, if there exist elements p and q such that x is p times q times p inverse times q inverse, then x is in the kernel of f. So this is an implication. Our goal currently is an implication. We've got to prove that A implies B, and now we've got to, you see what happens. We've done this lambda x. We now need to do this. Let's do this. Rintros pqw, and let's see what happens. Great. So we've made progress. We've got to try and prove that if there exists p and q such that x is p inverse times pq times p inverse times q inverse, if such a p and q exists, then x is in the kernel. So we do that, and now we see we've got p and q in G, and then we've got a theorem. Why is that called W? H. And now we've got a theorem called H that p times q times p inverse times q inverse is equal to x. And now we can see that x is irrelevant, right? X was a random element that used to be important, but now we know a formula for x. It's p times q times p inverse times q inverse, and we don't really want that to be x. We want that to be p times q times p inverse times q inverse. And we could rewrite H here with the arrow on the left and change x to p times q times p inverse times q inverse. But you know what? H may as well be used as the definition of x, right? X is just a random element of G. We don't know anything about it. And then H says that p times q times p inverse times q inverse is x. So why don't we change H to refl, right? And now the definition of x is p times q times p inverse times q inverse. And now our goal says that p times q times p inverse times q inverse is in the kernel. Okay? Which is great. This is great, right? We're up to here. The commutator is generated by things of the form x times y times x inverse. Okay, so this is great. So we just need to, commutator is generated by things of the form, so just need to, so just need to check our commutators, right? That's as far as we've got. So now we want to, where's our goal? Here we are. So now we want to apply f. We want to, right, we want that, what's the deal here? Our goal is to prove that this is in the kernel. So our goal is to prove that f of this is 1, right? Our goal is to prove that f of this is 1. And if we look, we've done all that. Yeah, you see, this is where lean broke. Lean tried to apply isGroupHom.memcur. And isGroupHom.memcur, it probably says, it says memcur, right? This lemma here will say that x is in the kernel of f if and only if f of x is 1. But the problem is that it's about an isGroupHom, and we don't want to do is stuff. We want to do GroupHom. So we want to rewrite something called memcur. But the thing is, we have a different implementation, right? We're not doing isGroupHom anymore. We're doing GroupHom, but we still should have the same specification. So there should be something called here we are. Look, there's something called monoidHom.memcur. Let's try rewriting that instead. That has not worked. Let's see what it says. MonoidHom.memcur. I see the problem. MonoidHom.memcur says x is in the kernel if and only if f of x is 1. But when we rewrite it, we get an error because it doesn't say that it's in the kernel. It's this stupid coercion. This kernel is a normal subgroup, but then we coerce it to be a set because we were doing something about things with sets. We need to get rid of this coercion. So let's just, let's just use normcast or something. There we go. Normcast has got rid of the coercion. Normcast deals with coercions. And now we can rewrite our monoidHom.memcur. And now we've got to prove that f of p times q times p inverse times q inverse is 1. Okay, that's great. And so now here's the proof of this. There, you can see they rewrote W because we don't have to do that. And now they try to solve this. They try to prove this with the simplifier. So I suppose we could take, we could kind of take the proof. We could try it. Comma might not work. Yes, it's failed to do it. Let's try the simplifier. Let's see what the simplifier does by itself. There we go. The simplifier has applied f. So now we've got to prove that f of p times f of q times f of p inverse times f of q inverse is 1. And this is now a statement about A, right? This is the crucial thing. P and q are in G, but f maps G to A, and the only places where P and Q appear are f of p and f of q. So now we've got to prove that in an abelian group A, if x times y, we've got to prove that in an abelian group A, x times y times x inverse times y inverse is 1, right? And that's obvious because we need to, I don't know, rewrite. Yeah, this is a pain because the R, listen, okay, look, lean is bad, right? Here's a weak point of lean, right? There's a tactic that proves things for commutative groups and it's called arbel. And arbel doesn't do it. Why doesn't, if I hover over arbel, look, arbel says evaluate expressions in the language of additive commutative monoids and groups. It attempts to prove the goal outright if blah, 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 blah. But unfortunately, arbel is for groups with an add, and this is groups with a times, okay? So we need to write a machine, computer scientists need to write a machine that changes this, that changes our arbel tactic and makes it work for multiplicative groups. I mean, this is a farce. Why doesn't this work? It's the same thing. So I'm going to have to, let's rewrite, I don't know, mul left com or something. Does that do something? No. Mul right com. Mul right com has worked. Now let's try the simplifier. Great, we've done it. Okay, so I've done it, but this is kind of annoying, right? Annoying that there was no com group tactic. Okay, that was the problem. The group tactic works for groups. So, and now the error says that there are no goals to be solved. And that has fixed that. And now let's remove, so now there's only one error, which is that we've got an exit. So let's get rid of the exit. And now we see we have another error, right? What is going on here? Is lambda f x, what's going on? This is broken. Let's highlight everything that's broken. Let's remove it completely, and let's replace it with a sorry. And now that's fixed. And now, okay, this is a breakthrough moment, right? This is a breakthrough moment because this is the first time that the file has been compiling with no errors, right? I really like the file has been compiling with no errors, so I'm tempted to push. There, why don't I just click here? I'll commit at least. There. No errors in refactored abelianization, but some sorries. There. I'll commit that. It's committed. And now let's see, so what's going on? I've got one warning. Let's go and find out what the warning is. We were reading this proof. So here we are. So the problem is with the next proof. The problem is with lift, right? Lift says, I see. If G is a group homomorphism, then it factors through GAB, right? So what's happening here is we are attempting to define, we've got a map from G to A, I see, we've got a map from G to A, we've just proved that the commutator is in the kernel, so now we want to deduce the existence of a map from G mod the commutator to A, and that's like the first isomorphism theorem or something. So let's have a look and see what this sorry is. Let's put begin sorry end so we can see what it is. We can put the begin down here and the sorry in the end. Let's take a look and see what this sorry is. Because if this is a proposition, this is great news, right? This is a proposition. F of x is 1. We're trying to prove. This is a maths problem, right? The reason it's not working is because there's a maths problem that needs solving. So let's solve this maths problem. Let G be a group. Let A be an abelian group. Let F be a group homomorphism from G to A. Let X be an element of G. And let's assume that X is in the commutator subgroup of G. We've got to prove that f of x is 1. Okay, that's what we've got to do. And now, how are we going to do that? Do you know what? I'm just thinking, well, x is in the commutator, so we may as well check for commutator. We just did that, right? We just proved some lemma that said this. Let's look at the proof. Where's the proof that didn't work? Oh no! The proof that didn't work, I've commented it out. I'm such an idiot. Where's the proof? There. Let's put that down there. And now let's go begin, sorry, end. Here's the proof that didn't work, because it will help us to prove this thing. X is in the commutator of G. We've got to prove that f of x is 1. And the first thing it applies is that the is group hom. You see, this is why it breaks here, because we don't have is group hom anymore. But we do have mem cur, right? We should have the same. Let's rewrite mem cur. Let's see what that says to us. Rewrite monoid hom dot mem cur. It's the wrong way. So let's rewrite it this way. Rewrite monogroup hom mem cur. So that's that first part there. And so the bit of the proof that we haven't looked at yet is this. Now let's have a look and see what the goal is. We now know that x is in the commutator, and we want to prove that x is in the kernel. So we would be done if the commutator was in the kernel, right? But the commutator being in the kernel is exactly what we just proved. Commutator subset cur. So the proof should use, you see the proof uses this. Let's apply commutator subset cur. There. And now the goal is that x is in the commutator, and the hypothesis is that x is in the commutator. So that's just an assumption. That's just an assumption. Let's put a comma at the end of that. And now we've got an error on the sorry. An error on the sorry is normally good news. It's either really bad news or really good news. An error on the sorry either means you've got your brackets so wrong that everything's completely confused, or it means that the goal is closed and there are no, look, when you get there are no goals to be solved. That's the best error. So we delete the sorry, and there we go. So now we can delete that proof. We were inspired by the proof, but now it can go. And now are there any more errors? There's one more error. Oh, because I've deleted a bracket there. And now there are no errors at all. There are no warnings. So I will finish by, you see this proof was sophisticated. This proof was sophisticated, so it survived the refactoring. And let's see what it says. It says that there's a unique lift. It says if I've got a random group homomorphism G is such a lousy name for a group homomorphism, right? Let's call it phi. Let's say I've got a random group homomorphism phi from G to A, and let's have H phi that says for all x in G, phi of G bar. Remember, of x is G bar. X is a map from the abelianization for all x in G. I'll put for all x in G, right? For all x in G, phi of x, i.e. phi of the image of x in its abelianization, phi of x is f of x. Right. So this says that phi, remember what's going on here. We've just constructed, given a group homomorphism F from G to A, we've just constructed a map from the abelianization of G to A. And now it's saying, let's say we've got a random other group homomorphism from the abelianization of G to A, and let's assume that it agrees on all elements of G, then I claim that phi of x must be the thing that the universal property. You see, this is the data part of the this is the data part of the universal property. So this is the data part of the universal property of the abelianization, and this is the proposition part, right? This is the prop part. There. This is the theorem part of the universal problem. You know, the theorem that says that something is unique. There. So we've got this lemma lived of that says lived. We've got lived does what you think it does, and it does it by definition. And now let's just read this proof. So how are we going to prove it? Here's the proof. Let's see what the question is. Here's the question. Let's just see what let's just see what this is. This has got nothing to do with groups, really. This is just all about the universal property. This is all about the universal property of quotients, right? This has got, this just follows immediately from the universal property of quotients, because we know that phi agrees with f on the image of the quotient map, right? H phi says that phi agrees with f. H phi says phi agrees with f agrees with F on the image of G in GAB, right? That's what H says. H phi says this. And so what we need is simply proof that the image of G in F is, I mean, this is the point. We need to just check that the image of G in F is everything. And that's one of the universal properties of a quotient, right? This is now no longer got anything to do with groups. This is some universal property of a quotient, and indeed it's called quotient group.induction on. And you can read what quotient.induction on. It says, given a group and a subgroup and a property of the quotients, if it's true for everything, okay. If it's true for everything in the preimage, it's true for, it's just some, I don't know, it's just an inductive principle. It's not very interesting. We don't need to think about it. What we need the universal property, and this universal property has been proved by using the universal property of quotient groups. And so that's the end of that, and that's the end of that. And we have no errors and we have no warning, so I'm going to push again, right? Abelianization finished. Abelianization now compiles without deprecated import. And I'm gonna, yeah, why not? Let's just do that. Now let's do that. Let's cancel this. Oh, I've done it. Right. So that's been pushed. That's the end. Yeah, I've got lots of non-terminal sets. This needs tidying up, right? This whole thing needs tidying up. I mean, lots of other superficial work needs to be done. Like this, the doc string needs to be written properly. The doc string is not mathlib standards. We should explain what the definitions. We should document all the definitions up here. So that implementation issue warning is now gone. But I need to tidy up all of these. You know, I should take away all the silly comments, and I need to deal with the non-terminal synths. I mean, in fact, you want to just deal with them now? I'm going to stop streaming, but let's just deal with them now. Blah, 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 blah. That show we probably don't need. That can go, I should think. Yeah, that desync could probably go. Yeah, there. What's going on down here? That desync could probably go. You know, you put these in so you know which tactic to use next. Normcast is fine. We use a non-terminal simp here, so we should fix that. Or maybe we could, I tell you what, can we do this? Can we get the simplifier to do everything? Blast. Simp mul right com. Let's just tell it to what to do mul right com on. What does mul right com even say? It says A times B times C is A times C times B. And what did we do here? The proof used to be simp rewrite, which is bad. No. It's simp, comma, this, there. And what did we actually rewrite? Did we rewrite f of p? Is it this? F of q. Does that still compile? That still compiles. So why don't we tell the simplifier this? Use mul right com, but only on that. And now that's done it. You see, it says goals accomplished. So that can all go, and we can finish it like that. So, you know, and that's nice. Monoid hom mem cur. Is that a simp lemma? Is this? I'm just now wondering. You see, now what I'm doing now is not mathematics, right? I'm now refactoring. I'm responding to Babek's comment. Let's print monoid hom mem cur. It is, if you look here, you can see all the attributes. Two additive. Okay, it's not a simp lemma. So why don't we add monoid hom mem cur to the list of simp lemmas we're allowed to use, and let's not rewrite it here. And that's still good, right? You see, what I'm trying to do is I'm trying to turn the proof. You see, that was the proof that started, right? What's happening is I'm turning my new proof back into this old proof. And now normcast, you see, maybe, so why don't I try this there? Would that work? Ah. Is that not a thing for normcast? Can you not tell normcast? Oh, I didn't know that. You can't tell normcast things. But I'm wondering, would the simplifier, let's try this. I wonder whether the simplifier, what did normcast actually do? It was just some stupid arrow, yeah. F was in some, there's an invisible arrow, and it's a coercion, so I just use normcast to get rid of it. Why don't we just comment this out? The simplifier might know that. You see, the simplifier does know it. So I didn't know this. So now we don't ever need, you see, we don't need to move it, we don't need to go into tactic mode at all, right? Ah, there's this ruffle. Aha. So maybe it's best. Rintros is quite a powerful tactic. I've done this with Rintros simp. In the old days, it was being done with intros. Oh, that's, yeah, this is, my proof is better, right? Yeah, they apply the memcur, and then they have to do a stupid rewrite of this W, because in term mode you can't do this trick. Okay, I'm going to leave with tactic mode. I think this is fine. I think my proof is so now you see, now we've slightly obscured it, right? We've now got to prove that P times Q times P inverse times Q inverse is in the kernel, and now what we're saying is actually the simplifier can do that as long as you give it some clues. For example, memcur. Okay, so now is this? Okay, now I have no terminal simps. And this proof here, this is just silly, right? We could literally, this is literally apply a function, use a hypothesis. So this, let's do this one. It's monoid memcur. Let's exit here. I'm turning it back into a term mode proof. Monoid memcur something something, go square brackets. How about that? No, monoid memcur. Ah, I see. Monoid memcur dot one or something, or either dot. It's probably dot two, is it? Bingo. Monoid memcur dot two. So now we want to prove this thing. So now we want to run this. So maybe I'll put a dollar commutator subset cur. Maybe I'll put a dollar commutator subset cur something. Great. And now we can see that what we need is that x is in the commutator of g, and that's 8. So let's put h there, and there we go. So you see what I did there? I took our lovely, I've taken our lovely term mode proof, and I've butchered it, right? I've taken our lovely tactic mode proof that we could read, and I've completely butchered it, so now it's an unreadable term mode proof, but they'll like it like that in mathlib. There, and that proof I didn't touch. Okay, I'm going to push again. Now, if any of you people watching, now Rintros is just, yeah, probably, did I do an intros and a Rintros? Yeah, thank you. There. Thank you, anonymous commenter. You just contributed to mathlib. I'm going to now push this. So first, first attempt at tidying. Still need some tidying. Tidying and a doc string. Okay, so I'm stopping now because I've spoken for quite some time. I'm going to push this. So if you want to help this branch is completely broken, right? I showed you Sulov's theorems. The Sulov's theorems branch is broken. Like loads and loads of files are broken. Okay, and all you have to do is you have to find the files which are broken, but all their imports, none of their imports are broken, and then you have to fix them. Okay, so we're just slowly doing this, and it's really good fun. It's called the subgroup implementation refactor. It's called the subgroup refactor issue. A refactor is when we leave the specification the same, but we change the implementation. We're currently changing the implementation of subgroup, and it just means we have to fix some proofs. But the proofs in here were really kind of nice high-level proofs. So it's quite good fun fixing them. And if anyone else wants to join in, as far as I'm concerned, I spent the last hour playing a computer game. You see, and so if you want to play the same computer game, the branch is called quotient group refactor. And if you do lean project get mathlib, there's even a way of doing it. You can even do lean project get mathlib quotient group refactor somehow. There's some syntax, I've forgotten how. You can get that, and then you've got a broken mathlib and try and fix it. And if one of your imports is broken, try and fix the import first. Because if the imports are broken, then stuff might not be there. You know, the interface you need might not be there. But find a file where the imports work, where it doesn't work, and then just fix it and push. It's really good fun. Right, that's quite enough from me. Thanks for watching, and I will stop.